The land masses that compose Turkey, namely the Anatolian and Thracian peninsulas, were formed from sediments of the Tethys Sea during the Mesozoic era, a time when dinosaurs roamed the earth. It's important to note that in Turkish sources, the Mesozoic is referred to as the second geological period. Dinosaurs were terrestrial creatures, which means they lived on land, died on land, and became fossilized in terrestrial deposits. Just as we don't find elephants that die in the sea today, dinosaurs also left their fossils on land. While there are marine fossils in Turkey as old as the dinosaur fossils themselves are primarily found in terrestrial rock formations. This distinction highlights the unique geological history of the region. Turkey's geological history encompasses a wide range of geological time periods, which implies that significant events related to these periods have occurred on these lands. This diverse geological history has endowed our country with a wealth of geological and geomorphological features. Examples of this wealth include the presence of coal deposits formed during different geological periods in the Paleozoic era and coexisting lignite deposits in the Cenozoic era. Turkey's geological diversity and the coexistence of different geological formations make it a region of great geological significance. In Turkey, areas belonging to the first geological time period, the Paleozoic era, are not particularly common. However, during this era, there were the formations of sedimentary and metamorphic lands in regions such as Zonguldak, Alanya, Anamur, Mardin, Aydın, the Olds Mountains, and the Biga Peninsula. Additionally, it is noteworthy that dense forests flourished during the Carboniferous period within the Paleozoic era due to humid climate conditions. As the waste and organic matter from these ancient forests accumulated in basins, they gave rise to the formation of coal deposits, notably in Zonguldak and Bartın. This geological history sheds light on the formation of valuable coal resources in these regions. Taking into consideration its geological history, Turkey was situated beneath the Tethys Sea approximately 200 million years ago. Over time, due to tectonic plate movements, the land where our country is located gradually emerged above the water surface. Turkey is surrounded by the Eurasian Plate to the north and the African and Arabian Plates to the south. The Eurasian Plate, being the largest of these plates, moves at a relatively slower pace. In contrast, the African Plate experiences a movement of around 10 mm per year, while the Arabian Plate moves approximately 20 mm northward. Consequently, the Anatolian Plate finds itself wedged between these massive tectonic plates and is pushed to the west at a rate of about 20 to 30 mm per year. This complex interplay of tectonic forces has contributed to Turkey's unique geological and geographical characteristics. Paleozoic lands in Turkey include various geological formations and regions, some of which are Bitlis Massif, Kırşehir Massif, Olds Mountain Massif, Sarıglan Menteşe Massif, Dağ Divriği Massif. In addition to these massifs, Turkey is also known for its coal deposits, which have formed over geological time periods and are of significant economic importance. These geological features contribute to the country's rich and diverse geological heritage. The Mesozoic lands of Turkey are marked by significant geological events, including the closing of the Tethys Sea, leading to orogenesis, mountain building processes, the formation of karstic rocks, which are characterized by distinctive landforms resulting from chemical weathering and erosion, such as caves, sinkholes, and limestone pavements, volcanic activities in regions like the West and East Black Sea. These geological processes have played a crucial role in shaping Turkey's geological landscape and have left their marks on the country's unique geological and geographical features. In the Cenozoic era, Turkey experienced significant geological developments, including the formation of salty sedimentary rocks, which are created through the accumulation of mineral-rich sediments, the presence of lignite deposits, which are a type of low-rank coal, the occurrence of oil deposits, highlighting Turkey's hydrocarbon resources, the deposition of lake sediments in various regions, widespread volcanism, resulting in the formation of volcanic mountains like Hasan, Erciyes, Agar, Supan, Kula, and more. These geological processes have contributed to the country's diverse geological and geographical features and have made Turkey an area of geological significance. During the Quaternary period in Turkey, several significant geological events took place, including volcanism, which continued to shape the region's geology. The collapse of the Aegean land, leading to changes in the landscape. The formation of straits, which are narrow bodies of water separating landmasses. The development of alluvial lands, including plains and deltas, due to sediment deposition. The presence of major fault zones, such as the North Anatolian Fault Zone, East Anatolian Fault Zone, and West Anatolian Fault Zone, which are associated with seismic activity and earthquakes. These geological processes have had a profound impact on Turkey's geological and geographical characteristics, making the region geologically dynamic and prone to seismic activity. The perigenic movements in geology refer to the gradual uplifts or depressions of large land masses with long wavelengths, typically characterized by broad undulations rather than intense folding. These movements primarily affect the broad central regions of continents, known as cratons, and are considered part of a perigeny. The perigenic movements can take the form of subsidence, where the land sinks or moves lower, or uplift, where the land rises. These movements are driven by a combination of forces acting along the Earth's radius, including factors related to isostasy, the equilibrium of forces within the Earth's lithosphere, and faulting within the Earth's crust. In the context of Turkey's geological history, perigenic movements have played a role in shaping the country's landscape and topography over geological time periods. In the context of geology, orogenetic movements refer to the processes that lead to both structural deformation and compositional differentiation of the Earth's lithosphere, which includes the Earth's crust and the uppermost portion of the mantle. These movements typically occur at convergent plate margins, where tectonic plates are colliding or interacting. An orogeny, also known as an orogenic event, is a geological phenomenon where a continental plate crumples and is uplifted, leading to the formation of one or more mountain ranges. Orogenies involve a series of complex geological processes collectively referred to as orogenesis. In Turkey, as in many other regions with active tectonics, orogenetic movements have played a significant role in shaping the country's geological landscape. These movements are responsible for the formation of mountain ranges, the deformation of rocks, and the creation of geological structures. Turkey's unique geological features are a result of the orogenetic processes that have occurred over geological time periods. Volcanism in Turkey, as in many other regions, is the geological phenomenon characterized by the eruption of molten rock, known as magma, onto the Earth's surface or the surface of a solid surface celestial body, such as a planet or moon. This eruption process involves the release of lava, pyroclastic materials, such as ash and pumice, and volcanic gases through an opening or fracture in the Earth's surface, which is referred to as a vent. Volcanism encompasses all the geological phenomena associated with the movement of magma within the Earth's crust or mantle, as it rises to the surface and solidifies, forming various types of volcanic rocks and landforms. In Turkey, volcanic activity has left a lasting imprint on the country's geological history and landscape. There are several volcanic regions in Turkey, each with its own unique features and volcanic products, such as lava flows, volcanic cones, and calderas. Volcanic eruptions in Turkey have contributed to the diversity of landforms and geological features, making the country a region of geological significance. An earthquake, also referred to as a quake, tremor, or temblor, is a natural phenomenon characterized by the sudden shaking of the Earth's surface. This shaking results from the abrupt release of energy within the Earth's lithosphere, leading to the generation of seismic waves. Earthquakes vary in size and intensity, ranging from those so mild that they go unnoticed to those so powerful that they can launch objects and individuals into the air, causing widespread devastation across entire cities and regions. The term seismicity or seismic activity is used to describe the frequency, type, and magnitude of earthquakes that occur in a specific geographic area over a given period of time. The study of seismic activity and the understanding of earthquake mechanisms are crucial for assessing and mitigating earthquake hazards and ensuring the safety of populations living in regions prone to seismic events. In geology, a fault is a planar fracture or discontinuity within a volume of rock, and it is characterized by significant displacement caused by the movement of rock masses. These movements can result from various geological processes. Large-scale faults within the Earth's crust are primarily a consequence of the forces associated with plate tectonics. The most prominent faults often mark the boundaries between tectonic plates, such as subduction zones or transform faults. The interaction and movement of these plates along these fault lines can lead to substantial geological changes. One significant consequence of the activity along these fault lines is the release of energy, which is responsible for the majority of earthquakes. The rapid movement and shifts in rocks along active faults generate seismic waves and vibrations that manifest as earthquakes. It's important to note that not all fault movements result in sudden and violent earthquakes. Some faults exhibit slow, gradual displacement, a phenomenon referred to as aseismic creep. Understanding faults and their behavior is crucial in the field of geology, as it plays a vital role in the study of earthquakes, the Earth's tectonic activity, and the geological processes that shape the planet's surface. In seismology, the terms hypocenter and epicenter are commonly used to describe specific locations related to earthquakes. Hypocenter, or focus, the hypocenter is the point within the Earth where the actual fault slip or fault rupture occurs, resulting in the release of seismic energy. It is the underground origin of an earthquake, often located deep beneath the Earth's surface. The depth of the hypocenter can vary for different earthquakes. This is the point where the seismic waves originate. Epicenter, the epicenter, on the other hand, is the point on the Earth's surface directly above the hypocenter. It's the location where the seismic waves first reach the Earth's surface. This is the point usually reported in terms of latitude and longitude when describing the location of an earthquake. The intensity of shaking at the epicenter is typically the strongest. So, the inner center and outer center you mentioned correspond to the hypocenter and epicenter, respectively, in the context of seismology and earthquake analysis. That's correct. In geological terms, when tectonic forces cause the Earth's crust to deform, hard layers of rock that cannot bend can undergo breakage along specific planes or fault lines. These fault lines represent areas where the rock has fractured due to the immense pressure and stress caused by the movement of tectonic plates. The separated pieces of rock on either side of the fault then move away from each other, not only horizontally but also vertically. This movement results in the formation of a fault, which is a planar fracture or discontinuity within the Earth's crust. Faults play a crucial role in the Earth's geological processes, including the release of seismic energy and the occurrence of earthquakes. The study of faults and their behavior is essential for understanding tectonic plate movements, earthquake activity, and the broader field of structural geology. Normal fault, a dip-slip fault in which the block above the fault has moved downward relative to the block below. This type of faulting occurs in response to extension and is often observed in the western United States Basin and Range Province and along oceanic ridge systems. Reverse, thrust, fault, a dip-slip fault in which the upper block, above the fault plane, moves up and over the lower block. This type of faulting is common in areas of compression, such as regions where one plate is being subducted under another as in Japan. When the dip angle is shallow, a reverse fault is often described as a thrust fault. Strike-slip fault, a fault on which the two blocks slide past one another. The San Andreas fault is an example of a right lateral fault. A left lateral strike-slip fault is one on which the displacement of the far block is to the left when viewed from either side. A right lateral strike-slip fault is one on which the displacement of the far block is to the right when viewed from either side. What are seismic waves? Seismic waves are caused by the sudden movement of materials within the Earth, such as slip along a fault during an earthquake. Volcanic eruptions, explosions, landslides, avalanches, and even rushing rivers can also cause seismic waves. A P wave or a primary wave is one of the two main types of elastic body waves, called seismic waves in seismology. P waves travel faster than other seismic waves and hence are the first signal from an earthquake to arrive at any affected location or at a seismograph. P waves may be transmitted through gases. In seismology, S waves, secondary waves, or shear waves, sometimes called elastic S waves, are a type of elastic wave and are one of the two main types of elastic body waves, so named because they move through the body of an object, unlike surface waves. S waves are transverse waves, meaning that the oscillations of an S wave's particles are perpendicular to the direction of wave propagation, and the main restoring force comes from shear stress. Therefore, S waves can't propagate in liquids with zero, or very low, viscosity, however, they may propagate in liquids with high viscosity. In seismology, love waves, also known as Q waves, Care, German for lateral, are surface seismic waves that cause horizontal shifting of the Earth during an earthquake. Augustus Edward Hough Love predicted the existence of love waves mathematically in 1911. They form a distinct class, different from other types of seismic waves, such as P waves and S waves, both body waves, or Rayleigh waves, another type of surface wave. Earthquakes are recorded by a seismographic network. Each seismic station in the network measures the movement of the ground at that site. The slip of one block of rock over another in an earthquake releases energy that makes the ground vibrate. How the earthquakes are measured. How are earthquakes measured? Magnitude and intensity scales, CEA. A seismograph is the primary earthquake measuring instrument. The seismograph produces a digital graphic recording of the ground motion caused by the seismic waves. The digital recording is called a seismogram. A network of worldwide seismographs detects and measures the strength and duration of the earthquake's waves. Earthquake magnitude scale. An important piece of information to keep in mind is that the magnitude scale is logarithmic. In other words, it is comparing amplitudes of waves on a seismogram, not the strength, or energy, of the quakes, according to USGS. This helps us understand that while the size, amplitude, differences between small and big quakes are big enough, it is the strength, energy, differences that are meaningful. Try out USGS's How Much Bigger? Calculator to learn more about how to measure the magnitude of an earthquake. The Richter scale. From 1935 until 1970, the earthquake magnitude scale was the Richter scale, a mathematical formula invented by Caltech seismologist Charles Richter to compare quake sizes. The Richter scale was replaced because it worked largely for earthquakes in Southern California, and only those occurring within about 370 miles of seismometers. In addition, the scale was calculated for only one type of earthquake wave. It was replaced with the moment magnitude scale, which records all the different seismic waves from an earthquake to seismographs across the world. Richter's equations are still used for forecasting future earthquakes and calculating earthquake hazards. How is earthquake intensity measured? A second way earthquakes are measured is by their intensity. Earthquake intensity measurement is an on-the-ground description. The measurement explains the severity of earthquake shaking and its effects on people and their environment. Intensity measurements will differ depending on each location's nearness to the epicenter. There can be multiple intensity measurements as opposed to one magnitude measurement. The modified Mercalli scale. The modified Mercalli, intensity scale is used in the United States. Based on Giuseppe Mercalli's Mercalli intensity scale of 1902, the modified 1931 scale is composed of increasing levels of intensity that range from observable quake impacts from light shaking to catastrophic destruction. Intensity is reported by Roman numerals. An earthquake intensity scale consists of a series of key responses that includes people awakening, movement of furniture, damage to chimneys and total destruction. In the first geological time, which is the Paleozoic era, several land masses and geological features can be identified in Turkey. Some of the notable ones include Bitlis Massif, Kırşehir Massif, Olds Mountain Massif, Sarıglan Menteşe Massif, Dağ Divarikani Massif. Coal deposits. During the Paleozoic era, these land masses and geological formations were shaped by various geological processes and events. Coal deposits, in particular, are significant resources that have formed during this period and have been of economic importance. These geological features provide insights into Turkey's geological history and its rich natural resources. During the second geological time, which is the Mesozoic era, several geological developments and land features are observed in Turkey. These include: the Tethys Sea begins to close. During the Mesozoic era, the Tethys Sea, which once covered parts of present-day Turkey, began to close as a result of tectonic plate movements. Orogeny refers to the process of mountain building through tectonic forces. During the Mesozoic era, orogeny events would have led to the formation of mountain ranges in various regions of Turkey. Formation of karst rocks. Karst landscapes are characterized by unique landforms created by the dissolution of soluble rocks like limestone. The Mesozoic era may have contributed to the formation of karst features in Turkey. Volcanism, Western and Eastern Black Sea. The presence of volcanic activities in both the Western and Eastern Black Sea regions suggests that volcanic eruptions and the deposition of volcanic rocks occurred during this geological time. These geological events and features have left their mark on Turkey's landscape and geological history, providing valuable insights into the country's geology and natural history. The Cenozoic era, the third geological time period, brought about significant geological changes and land formations in Turkey. Some key developments during this era include: formation of saline gypsum rocks. The Cenozoic era saw the deposition and formation of saline and gypsum rocks in various regions of Turkey, which are often associated with evaporative environments. Lignite deposits. Lignite, a type of low-grade coal, was formed during the Cenozoic era in Turkey. Lignite deposits are valuable energy resources. Oil fields. The Cenozoic era also witnessed the formation of oil fields in Turkey, contributing to the country's energy resources. Lacustrine sediments. Lacustrine sediments refer to deposits formed in lake environments. Turkey's geological history includes the formation of such sediments in certain areas during this era. Volcanism, volcanic mountains, Hasan, Erciyes, Agar, Supan, Kula, the presence of volcanic mountains and volcanic activities during the Cenozoic era is notable. These volcanic mountains, such as Hasan, Ershais, Agar, Supan, and Kula, have shaped the country's landscape. The Cenozoic era has played a significant role in shaping Turkey's geological features, including its mineral deposits, energy resources, and volcanic landscapes. These geological events have had a lasting impact on the country's geology and natural history. The Quaternary period, the fourth geological age, brought about several notable geological changes and land formations in Turkey. Some key developments during this era include volcanism. Volcanic activity continued to be a significant geological feature during the Quaternary period in Turkey. This period witnessed volcanic eruptions and the formation of volcanic landscapes in various regions. Collapse of Aegean land. The Quaternary era saw the geological event known as the collapse of the Aegean land. This event had a profound impact on the region's topography and contributed to the formation of the Aegean Sea and the surrounding landscape. Formation of straits. The geological processes during this era led to the formation of narrow water passages or straits, which have had important geographical and environmental consequences in Turkey. Alluvial lands, plains deltas. Alluvial lands, characterized by sediments deposited by rivers, were formed during the Quaternary period. These areas, including plains and deltas, have been important for agriculture and human settlement. Fault lines and earthquakes. The Quaternary era is known for the activity of significant fault lines in Turkey. The North Anatolian Fault Line, Eastern Anatolian Fault Line, and Western Anatolian Fault Line have contributed to seismic activity and earthquakes in the region. The Quaternary period has played a crucial role in shaping Turkey's geology, including its volcanic landscapes, landforms, and seismic activity. These geological events have had both geological and societal implications for the region.